Okay, so let me continue. So last week I talked about two continuous problems. This talk, I think, still going to be something about non-converse optimization, except that I'm going to discuss one discrete problem. And similar things happen. Maybe you don't have to do a very smart way of lifting to converse problems. What you can probably do is just to solve the non-converse problem directly. And under nice statistical models, actually, very simple algorithms work in a very impressive way. Okay, so I'm going to focus on one discrete problem, but actually it can be significantly generalized to a lot of different settings of practical interest. Okay, so the problem is it's the following. So suppose I have n unknown variables, x1 to xn. Suppose that each of the variables is discrete, and it can take at most m possible values. Okay, so from 1 to m. Let me write it here. So I have x1 to xn. Each of them takes value from 1 to m. So it's something that falls on some finite alphabet. Okay, so if you look at this picture, this example, where xi can take values from 1 to 12. Okay, so I have each clock represent one values there. So the problem that I'm looking at is a case when you have a lot of such variables. So imagine that you have a lot of different clocks, but you don't know any of them. You want to simultaneously recover all of these values. Of course, if I want to do this job, I want to have some measurements. And the kind of measurements that I'm going to focus on is the so-called pairwise differences. It doesn't have to be this way, but this is probably the simplest thing that I can use to motivate my problem. Okay, so imagine that every time I'm going to take a measurement, let's say between the node I and node j, and what I observe is some modulo difference. Xi minus xj modulo the alphabet size m. And of course, you have some noise, so it's corrupted by some noise. Okay, so this is a very simple model, but suppose I get a collection of such pairwise measurements. As a concrete example, this is probably one of the simplest examples I like to use as a guiding thread throughout this talk, is that, so maybe every time when you try to measure the pairwise difference, with some probability pi naught, you get to see the truth. Otherwise, you see some random, you flip a coin, so it gives you some random measurements. So I call this pi naught a non-corruption rate, because this is a probability that you get something useful. Otherwise, you get something completely useless. Okay, so this is an example of this model. And my goal, of course, is to recover all of the xi's, and based on this set of measurements. And this one small thing that I like to mention is that because I'm only measuring the pairwise difference, you won't be able to recover everything because you don't really know what is the global offset there. For example, if you add 1 to each of the xi, it will give you the same measurements. So our goal is to recover everything up to some global offset. Okay, so this is a model. So why is this something of interest to us? One of the probably simplest example is something coming from community detection. Okay, so in a lot of biological or social networks, the users in the social networks naturally can be categorized into multiple clusters. For example, in the stochastic block model, which is very commonly used to model social networks, you might have two different clusters. And then depending on whether the two users are in the same clusters or different clusters, they might have different friendship statistic or something like that. And the community recovery problem is basically about if you are only observing some kind of friendship or similarities between pairs of users, how are you going to partition them into multiple clusters? So if you really have only two clusters, and And if the similarities or friendship are only based on the membership between two users, and then this can basically be categorized as one special example of the pairwise differences model that I mentioned. Okay, so if you're a biologist, you probably have come across this very important application in genomics. This is something called haplotype phasing in genome sequencing. So each of the human being has 23 pairs of chromosomes. This is something that we already learned from Biology 101. One paternal, one maternal. Okay. So your paternal, these two sequences are usually almost identical, except for a few documented positions where you see some variance. And these variants determine the characteristics of each human being. Okay, so, and these are the parts where the two sequences differ. They call them SNPs. Okay. So the phasing problem is about the following. So I would like to know whether this variant comes from your dad or comes from your mom. Okay, you inherit them from your parents. We want to know where this comes from. And for example, if this variant comes from your dad, you can say, okay, you can encode xi as 1. Otherwise, you encode it as 0. So it's a 1-bit information there. Now, in the sequencing technology, sometimes they have this kind of very special technology that give us some kind of pairwise read. So this is sometimes they are going to simultaneously touch two of the SNPs, and then what they can only tell you is that are they on the same chromosome or not. Okay, so this is some kind of mechanism that physicists can tell us. Now, based on this kind of pairwise information, the goal is to try to figure out all of the xi information, which they call phase information. Okay. So this is a very fundamental problem about haplotype phasing, which is very important in developing some personalized medicine in biology. Okay, so moving away from this genome sequencing, another very fundamental example comes from computer vision, computer graphics, and actually sometimes structural biology. So this is the problem about how to jointly align a collection of images which reflect roughly the same physical objects. For example, so now I have a few car models. Okay, so these are some shapes models that you have on your computer, and each of the cars is rotating some arbitrarily. Now, one of the very, very important tasks is about how to jointly align all of these car models based on some features you have. Okay. So this is one of the most important tasks when you try to do any kind of computer vision and computer graphics tasks. So what computer vision people are doing, a popular paradigm is the following. So what they are able to do, so it's very difficult to jointly align all of them. So what they are going to do is to first start by try to align a pair of the cars. So every time they look at a pair of the models, they try to find some way using raw features to align them. So which basically figuring out what's the relative angle between these two cars. And after that, they are going to have a collection of possibly noisy pairwise measurements, and then they are going to use another algorithm to jointly refine all of these pairwise estimates. Okay, and so this is exactly one of the problems I describe as a joint alignment from pairwise differences. And there are other things I'm going to skip. If you're interested, feel free to talk to me offline about any of these. So how are we going to solve these fundamental problems? Very naturally, we are going to start with some mathematical estimation. So basically, suppose that or mathematical estimation or empirical risk minimization. So basically, let's assume that we have a collection of pairwise measurements, but suppose that they are independently corrupted. And if we make these assumptions, we can probably write out some kind of log likelihood function for each of the pairwise measurements So basically, you are maximizing some log-likelihood function, which is a superposition of all of these pairwise log-likelihoods. There is an important constraint, is that each of the xi takes some discrete value. So it takes value from 1 to m, okay? But this is a very generic maximal likelihood estimation problem. In general, this is going to be very, very difficult, as you can imagine. First of all, the log likelihood function can be arbitrary, okay, depending on what the noise model you have. So it could be very, very complicated. So complicated that maybe it's not that friendly for optimization purpose. Second of all, the input space is sort of like, discrete to start with. So this gives us a discrete optimization problem, which is in general, very, very difficult to solve in a reasonable time. And because of all of this, the problem looks, scary at first sight. But we try to make some progress towards this. We're trying to say that actually not all of these, not all of the problems like this are difficult. Maybe if you have a nice statistical models, this is actually something that can actually be solved using very, very simple paradigm. Okay, so this is our procedure. What we are going to do, the first step is to try to change the parameter space a little bit to make it slightly easier for us to do optimization. So what we propose is something extremely simple. So since I have xi ranging from 1 to m, let's use a collection of standard basis vectors to represent them. So if xi equal to 1, let's use the first standard basis vector to represent it. If xi equals to 2, use the second basis vector. No, sorry, this should be E2 here, actually. So I have a collection of them, but I'm going to use a collection of orthogonal standard basis vectors to represent each of the values. Okay. So I'm doing a little bit of lifting, but try to do things in a high dimensional world. Okay, why do I do this? Actually, this is not the main reason I do this. The main reason is for me to encode an arbitrary log likelihood function in a slightly more intelligent way. Okay, so I have a complicated log likelihood function, L, for each pair, but xi can take m values, xj can take another m values. And because of this, I can actually enumerate all possible values of the log likelihood functions by a m by m matrix. So basically, I can use a matrix m by m to encode all possibilities of this log likelihood function. Okay? And just an example, if you have this random corruption model, you have actually, if this is the model, the log likelihood function can just read like this. Something very simple. But this can be arbitrary. The log likelihood function can really be arbitrary, but we have a way to encode them using an m by m matrix. So why do I consider this, augmented representation of the log likelihood function? The reason is that this, together with our representation for xi, allows us to represent this log likelihood function, an arbitrary log likelihood function, via some quadratic form. Okay, so this is this is extremely simple thing, but this turns out to be useful. We try to map arbitrary log likelihood function to a quadratic form. Okay, and quadratic is something that we're more familiar with, so we'd like to start with that. Okay, so and of course this is only for a pair xi and xj. I have a lot of different pairs. So I can stack all of them together to build a huge matrix capital L to incorporate all the information into this large matrix. And then this is basically saying that, okay, my original maximum likelihood estimation problem can be equivalently converted to this constraint quadratic problem. So except that, now the only thing that we do is that, okay, we want to impose some discrete constraints there. Okay, so far, this looks like a simple conversion of the problem. But actually, I have not really done anything, actually. So this problem is at least as difficult as the original one. So I'm not really making any progress yet. Fortunately, because we are more familiar with the quadratic problem, so maybe there are some message that we already learned from some simpler quadratic problems that can give us some hint about how to solve the problem. Okay, so we're going to start with this and illustrate how to solve the problem. So for problems like this, perhaps the easiest problem is about principal component analysis or eigen decomposition, whatever. So if you want to solve this problem, a very natural way is to do power method. Okay, so basically, since L is my data matrix in some sense, what I can do, if you are not familiar with power method, basically every single time I multiply my current iterate by this data matrix, I normalize it and continue. I repeat this procedure. So this is sometimes called power iterations. Continue doing this until it converges, and then we are done. Okay, so for this particular problem, this is tractable. Even though this looks like a non-convex problem, this is tractable, and we can actually use this extremely simple paradigm to solve it. So now I have a constraint PCA problem, except that I'm adding some additional constraints here. So maybe what we can do is to just also trying to do something like power method, except that I'm adding some, extra projection operations there. We add some constraint to make sure that we are always staying within the space that we're comfortable with. Okay, I'm going to discuss this a little bit, but basically this is a paradigm that we're going to use. Okay, so now the only thing that I need to specify is the projection operator. So there are many, many different ways to do projection. I'm going to single out maybe one or two versions for you. One way is that since I know that my xi falls within this subspace, this set of m vectors, sometimes I might consider to say, okay, let's try to conversify this set and then project to this conversified set. And if you conversify this set of standard basis vectors, it will give you a probability simplex. So it looks like this guy. And then you can do some projection onto the simplex and move forward. Sometimes, if you are more aggressive, you can maybe just project it onto this set, this discrete set. But for either strategy, actually, you can perform everything in time like at most m log m. So it's supposed to be something that's fast. Practically, it really depends on your problem. Sometimes this way this soft projection works better. Sometimes the hard projection works better. Okay. All right. Okay. So this is my algorithm. Now the next thing that I like to say is that this is my non-convex strategy. But there's one more thing: is that how are you going to start your algorithm? I do not think this is really needed, but this is the only thing that I can prove. I'm pretty sure that random initialization also works for this problem, but I can't prove that. So let me start with a simpler one, and to show that actually this strategy actually gives you a lot of information about the ground truth. So now try to look at this L matrix that I have built. So under the statistical model that I have, if the noise are ID, and after some proper permutation, you can show that if you look at the expectation of this matrix, this looks like this guy after permutation. So this looks like a low rank matrix, except that I'm missing some diagonal components there. Okay, so this is approximately low rank, and the rest looks like some random perturbation. And because of this, a spectral method, we can use a spectral method to get a good rough initial guess. The way we do it is the following. So I have this data matrix. I'm going to just compute a low rank approximation of this data matrix. And after we do that, let's just pick a random column. So basically, you pick a random column, and you project this column onto the space you're comfortable with. Okay. So this is an extremely simple initialization strategy, which we can guarantee that it gives you some rough initial guess. Okay, so in summary, this is what I propose. So first, I'm going to start with the spectral initialization. Again, this is probably not necessary. But the most important thing is actually I'm going to do projected power method until it converges. Okay. This is extremely easy to do, but it turns out that this is a strategy that works extremely well in practice. Okay. So to illustrate the power of this strategy, let me start by considering this extremely simple model that I mentioned, and then I'm going to generalize it to more complicated model. So again, just to remind you, this is a random corruption model that I have mentioned. Every time you measure a pairwise difference with some probability pi naught, I observe the ground truth. Otherwise, I observe some trash, okay, some basically uniform random noise. This is a result that we have. Okay, so as long as mu is a parameter that you can choose in the power iterations part, as long as you choose it to be not too small, then with high probability, projected power method that we propose recovers the ground truth within log n iterations. Okay, n is the total number of variables you have. As long as you can't have too high of a noise. So let's say the signal to noise ratio is not too small. And how to model that? And so in this model, I only have one parameter, pi naught. So if pi naught is 0, it means that you don't observe any useful thing. So pi naught needs to be sufficiently large. So suppose pi naught is larger than this guy, which I'm going to explain. And then the algorithm works fine. Okay, so let's try to see what this really means here. Okay.
In your algorithm, you assume that you know the matrix L, but your observation is Yij, which seems to be like a...
So that's a log likelihood function. So we are assuming that you know the log likelihood function.
Oh, okay.
So L, okay. So one thing is that I assume that I know L is a log likelihood function. L basically is like log likelihood. Something like log likelihood function. So now I'm assuming that I know the log likelihood function. But for this particular model, I don't even need to know this actually. It turns out that if you write out L, it's a very simple transformation that can completely get rid of this part. So you don't need to know pi naught. You don't need to know anything.
So sigma 2 of L is the second eigenvalue for the matrix?
Yeah.
So what if it's 0?
For this part, if m is larger than 1, it's not going to be 0. So you can guarantee that. So under this condition, you can guarantee that the second, so this L, the second largest singular value is quite large actually. If m is at least 2. If m is 1, there's nothing to do. Okay. Yeah. Okay. So this is a result. And we need this pi naught to be larger than this. So what does it really mean? Okay, so recall that pi naught is the fraction of the measurements that are not trash. Okay, so what does this mean? This means that even though a fraction of 1 minus pi naught, which is like this guy, if 1 minus that are all completely random, which means that completely useless, and the algorithm still works. So this somehow says that if n is very, very large, even though 99% of your measurements are corrupted, you can still recover everything. So at least this is not really that surprising because you take a lot of measurements. Even though most of your measurements are incorrect, you still have enough information to do all the recovery part. So this is probably not surprising, but that algorithmically, this seems to be something very powerful. Next thing is that you only take log n iterations for you to converge, and each iteration, you basically read the data once. So in total, this is like a linear time algorithm. And all of this works. It doesn't have to, we don't necessarily have to use the initialization strategy that I mentioned, as long as you can find some rough initialization that achieve, like 50% of them correct. And then you are fine. 0.5 is also just a crude estimate. You can even make it like 0.9 it should be fine. Okay. Now, empirically, this is the phase transition you see. So basically, we are plotting the success rate when I change the non-corruption rate pi naught. And this is a theoretical prediction, and this is the practical curve. The color part is the practical curve. So yeah, so basically, it seems that they kind of match in a very good way. Okay, so this is just for the non-corruption. This is a random corruption model. And this can be significantly generalized in the following way. Okay, so now I'm looking for general noise such that suppose that all the noise eta ij are IID generated according to some noise distribution p0. Okay, so except for the ID part, this seems to be the most general thing that we can think about. For example, if xi minus xj equal to 0, let's say this is exactly the noise distribution. Let's say it looks like p naught. Okay, if xi minus xj, the ground truth is 1, I need to shift it a little bit, so I'm going to get a shifted version of this distribution. Well, if xi xj is sufficiently large, maybe they look very different. So as you can imagine from these plots, it seems that the most difficult part is to distinguish, this and this. Okay, so because in this part, the two distributions really look very, very close to each other. So it's the hardest part for you to distinguish them. And because of this, maybe we can try to introduce some divergence metric to quantify the difference in terms of the probability. So what we can do is to maybe introduce the KO divergence between P naught and P1. P1 means the distribution when the ground truth is 1. I can use KO divergence to measure the difference between the ground truth case and the case when the ground truth is 9. Okay, so I have a set of KO divergence to measure, the different pairs of probability distributions. Now, what we can say is the following. Roughly under the same condition, you can say that the proposed algorithm works within log n iterations as long as the minimum KO divergence between any two distinct distributions exceeds this guy. Okay, so this is there's a concrete preconstant there which is 4. Okay. So this sort of makes sense because if we want to achieve this job, I really want to make sure there's a little bit of separation in terms of the noise distribution in order to make this work. Now the question is whether this is a good condition or this is it's a terrible condition. Okay, so let me start by saying that actually empirically this seems to match practice very well. If I have, let's say, some kind of Gaussian noise model, and then this is the red line is a theory, and then the rest is the empirical part. It seems that this phase transition matches the theory very well. And we can actually show that this is information theoretically optimal in the following sense. So this theoretical curve is really information theoretically optimal. So below this curve, our algorithm works. Above this curve, there's no algorithm work. So even if you are able to really find maximum likelihood estimate, it does not give you the right solution. And this curve, really, this boundary really is captured by 4 log n over n. So this is very sharp. Including the preconstant, everything's sharp. Okay. So far I focus on the case when the alphabet size is fixed. When alphabet size is larger, actually, this is actually becoming more tricky, actually. So suppose that now my alphabet size is, allowed to grow with n. Now what we can say is that at least for the random corruption model, we can say that the algorithm works if pi naught is larger than this guy. This is not information theoretically optimal. Information theoretically optimal one should be 1 over square root of m times n, something like that. But I don't think there is any algorithm that is known so far that allows you to do this job. And I conjecture that this is probably computationally optimal thing that you can do. So there seems to be a barrier, computational barrier between statistical limit and computational limit. All right. Okay, so let me skip this part. So coming back to my motivation, and like to say that this is actually a useful algorithm for the problems that I mentioned. So if you have, coming back to this image alignment thing, so let's try to take a quick look using some online data set from this ShapeNet, which is something similar to ImageNet actually, but focusing on the shapes part. You can use some off-the-shelf algorithm to compute, some kind of pairwise cost, not necessarily likelihood function, but some pairwise cost there, which actually is very noisy. Actually, the data can be very, very noisy. And after that, you run our algorithm. You can basically align all of them. So it's not difficult to do. Practically, it seems to be even working slightly better than the SDP solution, actually. So this is somewhat to my surprise. But the thing that's not surprising is that the algorithm runs much, much faster than, even though now there are only like 25 chairs there, it's already like significantly faster than that. If you have more data instances there, the difference is going to be, even more striking there. Okay, so this can, I would like to say that this can also be applied to many, many different kind of applications. There's one problem called join graph matching in computer vision. Basically, I have a set of images of the same thing. Each of them, for example, let me take 3 of them. I can take several feature points on each of the image. I would like to find corresponding features across different images. Okay. So if you just run some off-the-shelf, pairwise matching algorithm, it's going to give you some incorrect matching, actually. So these red parts, red lines, basically represent incorrect matches if you just do pairwise matching results. The green parts means they are the correct one. And then you can just use our algorithm to try to refine this all of these pairwise matching results, and you can see that you can significantly reduce the number of incorrect matches for this problem. So this is supposed to be very useful for some computer vision tasks. I have also something happening in MRI, so in the interest of time, I'm going to skip this. But basically, this is trying to say that the algorithm seems to be working extremely well for some fundamental 3D MRI kind of applications there. All right. Okay. So let me talk about one more thing, and then I'll conclude. So there's one issue, either in this problem or in community detection, things like that. There's one issue that people often ignore, which actually turns out to be very important in practice. It's something called sample locality. Okay. So what is this? Okay. So in most of the prior works, either for this joint alignment thing or for community detection, most of the people assume that it is equally likely or almost equally likely to take measurements between any pairs of nodes. Okay. So usually if you go to community detection talk, you will see some picture that looks like this. Basically, you randomly take a pair of nodes and you observe some measurements. But this is a huge issue in practice, actually. More realistically, you might only be able to, nodes are actually different. You might only be able to take samples between nodes that are not too far away from each other. Okay? So basically, there seems to be some geometric constraint there that preclude you from getting the ideal kind of random measurements. For example, in the genome sequencing applications, you have, you might need to deal with 10 to the 5 SNPs, but each read can probably only covers, a range no more than 100. So what does this mean in mathematics? Mathematically, this means the following. When I'm taking measurements, there seems to be some constraints there. And this constraint may be better modeled by some graph. Okay, so maybe this is the graph that I have. This is a constraint graph, meaning that I might only be able to take measurements when two nodes are not too far apart. If this guy is too far away from this guy, then there's no edges there, meaning that I might not be able to take any measurements between far away nodes. So a more natural sampling model should be the following. Okay, so I have some constraint graph, and then over this constraint graph, I'm taking some random measurements. So this is the more realistic kind of measurement model that I can have. Okay, so basically, it means that there are some pairs of nodes you will never be able to take any measurements. Okay. So this graphical constraint, which models some kind of locality, seems to be very important in particular biological applications. So this is what is studied in prior works. Most of the people assume that there's absolutely no constraint, so we are able to free to take any measurement between any pairs of nodes. But what I would like to argue that we should actually consider the graph like this, which has a huge, a lot of constraint there, which require us to change our algorithm accordingly. Now, there are several questions that we might naturally ask. For example, how many samples are really needed in order to recover all the nodes if we have such kind of locality constraints? Now, the question is, if we can hope to do this, and how are we going to change our algorithm in order to deal with this locality issue efficiently? If you just use what prior work tell you, for example, like converse realization, they can get some results. But usually the result depends on something called spectral gap. It's like the difference between the largest and second largest eigenvalue of some kind of graph-related matrix, which actually, it's a sufficient condition. But I usually think that this is not the best way for us to do things. Okay, so I would like to argue that if you can look at for some of the specific models that are commonly used in practice, maybe there are some nicer way to do that. So maybe we change the algorithm a bit, and then maybe we can get something much better. Okay, and it turns out that for a lot of commonly encountered graphical constraints, we can actually still achieve efficient recovery in a reasonable time without losing any kind of information theoretic optimality. Okay, so this is, let me just start by looking at this line graph, this generalized line graph, and tell you how are we going to do this. Okay, so simultaneously recovering everything seems to be difficult. Now let's try to maybe class them into, in this way. So maybe let's look at this small cluster and then try to first see whether we can do something within this cluster. And if you look at this small subgraph, actually this is basically the same thing as what we do for the complete graph case. And because of that, maybe we can just repeat what I have mentioned before. Let's try to use spectral method, or maybe some kind of projective power method, and to do this job. Okay, so let's run some spectral method to get some rough initial estimate of this. Okay, and we can do this. And this is also only just a small subgraph. We can do it for a lot of different subgraphs. For example, this subgraph, this subgraph, this subgraph. This. Okay, we can do it for each of them. Now the only thing is that since we're doing things in isolation, there is at least one bit of information that we haven't figured out, which is some kind of like global phase or global offset or some kind of that. So even though within the cluster maybe they seem to be they can be estimated in a roughly accurate manner, but across different subgraphs there is some global information that need to be retrieved. And because of this, maybe we can include a second step by saying that, okay, so maybe we can just look at our estimate here and our estimate here, try to use the part that are overlapping to figure out this global information. So usually the global information only like 1 bit or 2 bits, so it should be fairly easy to calibrate this global information. So basically I'm going to gradually correct all of these global information. And then everything put together, I don't have a very clean solution, but I have a roughly correct solution. So let's say 50% of them are correct now. And after that, I can just do projective power method, and then, or maybe gradient descent or something else, to continue to refine all the measurements. So I can do some successive refinement until it converges. And the main result says the following, actually. Even though you have like a ring graph or line graph or something like that, we can still make sure that this algorithm allows you to achieve information theoretic optimality precisely, including the pre-constant. So below this curve, nothing is possible, even if you don't have computational constraint. Above this curve, the algorithm achieves exact recovery there. Okay, and this curve, it's captured by this quantity. If you don't know what channel information is, it's some kind of like a channel exponent that you have in those channel bound kind of things. Okay, and what this is saying that for this graph, it seems that the information limits and the computation limits actually meet, and you can get it precisely. And there is some kind of insensitivity phenomenon there, which says that actually this quantity seems to be true for a lot of different spatially invariant graphs. What do I mean by that? Like, for example, if you have a complete graph, you need the same number of samples in order to do this. For ring, you need the same sample size. You can also go to small world graph, something like that. And roughly, you also need the same number of samples in order to achieve exact recovery. And the information and computational limits seems to be identical for many of such spatially invariant graphs. Which are these graphs? Are probably, this is particularly useful for social networks, and this is particularly useful for biology graph. Okay, empirically, this is the information theoretic limits you have, and then these are some practical empirical phase transition which seem to match the theoretical prediction in a very well manner. But it's very, very fast. Extension beyond the spatially invariant graph, you can have some variation, which is not really a problem, like some kind of lines that looks like this. You roughly have the same message, except that now your sample complexity might differ a bit. Okay, so this is, which is not very surprising. You can also go beyond pairwise measurements. You can have sometimes a measurement might simultaneously cover 3 different positions or something like that, which are totally fine. You roughly use the same design strategy, and you can get everything in a precise manner. Okay. So I'm going to skip the real data part, and let me just conclude. So under some statistical models, very simple non-convex strategy seems to be extremely efficient, even though this is a discrete optimization problem. And sometimes the information theoretic limits can be precisely achieved in linear time for a broad family of models. Okay, thank you very much.
I'll start with one, which is a Wildfield graph, maybe 48. Do you mind go to maybe the one after? Oh, sorry, maybe 47.
Okay.
Okay. So it seems like the method that you mentioned at the end, which is you do the clustering and then you align them into overlapping pieces, each one around the algorithm. Yeah. It seems like you have to somehow line up those clusters with overlapping ones to make it work. Yeah. Now, if it's great, so you do some other kind of patching in order to...
No, it doesn't have to be done in a very smart way. You just pick, maybe this one is a subgraph, this is a subgraph. So as long as there are some overlapping things, it's fine. It doesn't have to be done in a very smart way, just roughly correct. So you choose the subgraph to be roughly of the same size, otherwise roughly the same size, and making sure there are some overlapping things happening there, and that's fine. So the first round...
Sounds like there's a lot of subjectivity in applying this.
Oh, yeah. Because this is a first stage, and first stage I'm happy with just, let's say, like getting 50% of the variables correct. I don't really care about whether I get like 60 or 70, because I can use the final round to refine everything. So the first part, basically just to get something roughly correct, and it doesn't really matter how accurate this is.
suppose I want to read your proofs on the information theoretical bounds. You list the 3 papers in the end. Which of the 3 will be the best paper to start
Oh,
with?
the last one is an MRI paper, so it has nothing to do with theory. So I have an MRI application, so this is not useful. This one, both, you mean the information theoretic part? Or?
Yeah, the proof that you established.
Okay.
That,
so if you only care about the information theoretic part, actually, I think both of them have a small section about that. Actually, that part is fairly easy. So I have a lower bound and an upper bound. The lower bound is Fanon's inequality, actually. That's something like that. And the upper bound just analyze maximum likelihood estimate. If suppose that, assuming that you can do it. And that's probably take you 1 page. Each of them, I think, has something like that. So yeah, this one is probably easier, slightly easier. Yeah, just the model is easier. Okay.
Okay, well, if any questions